Yes, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In our discussion today, I'm going to look at the concept of statics and condition for equilibrium. Now, we have come across these specific terms in our previous discussion on the concept of, particularly the concept of equilibrium. Now, in our study today, we're going to look at basically a definition of the concept of statics, which basically is going to entail a study of forces which are in equilibrium. And of course, we had said that for this specific condition of equilibrium to be attained, these specific forces are going to be having a net of zero acting on an object. Now, we are given different illustrations for this particular case for the concept of equilibrium, whereby we had considered a range of forces which are going to be acting on an object, and we had given a various representation for vector addition of forces, which we said are going to be giving us various results, especially which are referred to as, of course, resultant forces. Now, in this case, we're going to look at a body at rest and try to see if the uniform motion of this specific body at constant velocity is going to be at equilibrium. And of course, we're going to consider some of the conditions which we are going to be attaching to this concept of equilibrium. Now, particularly, I'm going to use this specific illustration which I've given on the right side of my board, which is going to be consisting of an object that is rest at an inclined, of course, or a rest on a plane which is inclined horizontally at a specific angle. Now, I've just provided this information at the lower part of this specific illustration, whereby we're going to have a force of acting towards gravity in terms of weight. Now, this is going to be given as a mg, while the force normal to this specific surface is going to be given in terms of m. Now, there's going to be an element of the force of friction which is going to be acting and, of course, ensuring that the object is in place. And we're going to, in a way, try to show that basically the coefficient of friction of this particular force is given in terms of either greater than or equivalent to the tangent or the tan function of this specific angle of inclination, which we are giving as alpha. So in this case, we are going to look at this specific concept of statics, which I basically said that statics entail the study of forces which are at equilibrium. And in this specific case, of course, we can as well. So let's have this one as study of forces which are in equilibrium. And of course, we're going to look at different ranges of this specific concept of statics, especially for the various range of forces which we have looked at. And later on, we shall look at the statics of course, rigid bodies. Now, a body at rest, or the one in uniform motion, is going to be at constant velocity, which of course is going to be implying that this body is at equilibrium. And we're going to use to look at various conditions which are going to be attached to this specific concept of equilibrium. Now, for a particular, of course, a body to be at equilibrium, the vector sum of all the forces which are going to be acting on it going to be given as 0. And this implies that if we have a range of forces which are going to be acting on this specific object, the vector sum of all the forces acting on this specific object is going to be 0. And therefore, we can give that one in terms of perhaps this specific representation, whereby we're going to have this one given as that one. So which means that the sum of all the forces which are going to be acting on this specific body, of course, are going to be 0. And we're going to look at this type of forces considering that perhaps the three-dimensional Cartesian coordinate system, whereby if we're going to look at the forces which are acting with respect to the f, of course, the direction are equivalent to the forces acting with respect to the y, and respectively, we are going to have that one equivalent to the forces acting in the z direction. And the sum of all these forces are going to be giving us what we refer to as 0. So in this case, we will also look at the concept of torque, which we defined as a product of a force times the perpendicular distance of that specific, of course, a distance from the point of action. And the torque as well, I talked about this specific concept of a torque in terms of the moment of a force about an axis. And we had given it using this specific representation of tau. So in this case, we are going to have this torque represented by force times perpendicular distance. Perhaps we can give this one in terms of this perpendicular distance given in terms of r. Let's give this one in terms of r. And as we said, this specific distance is going to be perpendicular from the line of action given as that. So in this case, for conditions of equilibrium, we said that the sum of all the forces, vector sum of all the forces acting on the object is 0. And number 2 is that basically we can have this specific aspect of a torque, whereby, as I've said, the torque is going to be the moment of a force about the axis. And of course, we have said that this specific case for torque as well is going to be 0. And this is going to ensure that for aspects like angular acceleration about an axis, they are going to be basically given in terms of 0. So we can give this specific aspect of the summation of a torque equivalent to 0 as well as one of the conditions which are going to be given for us to establish this aspect of equilibrium. So in that particular case, therefore, we are going to look at this specific example which I have given and try to see that if this specific object is going to be balanced on this inclined plane, which has been, of course, inclined at an inclination angle of alpha, we are going to compute the coefficient of friction and basically show that the coefficient of friction is equivalent to the tan of or is equivalent to all the greater than the tan of alpha. And we are going to borrow from our previous discussion where we had looked at the concept of kinetic and static friction, and that is going to be giving us, in a sense, how we can evaluate this specific aspect of the coefficient of friction, which is equal to or greater than the tangent of course, alpha. So from our previous discussion, I had mentioned that basically we can have this static, this specific friction given in terms of static friction, and this is the force which is going to be ensuring, of course, the object which is going to be the force which is going to be applied on an object is going to be resisted from ensuring the object is in motion, and therefore friction is a force which is going to resist the concept of motion. Now we can give this aspect of a static friction, which is defined by an object at rest and a force being applied, whereby this force is going to ensure that the object does not move. So the static friction, we said it can be defined in terms of mu s, which is a coefficient of a static friction times the normal, which is going to be a normal force, as illustrated by this specific illustration. Then secondly, we had defined the concept of this specific aspect of friction, whereby we defined kinetic friction as the friction which is going to be experienced during the motion of an object after this aspect of static friction has been overcome. And therefore, we said that this basically is equivalent to the coefficient of kinetic friction times the normal given as that one. And in this case, we are going to see that for such an object which is going to be at rest, then therefore we are going to look at the coefficient of friction which is going to be existing in this specific setup. Now we are going to have this specific coefficient of friction given in terms of this specific aspect of friction is smaller than or equivalent to this going to be the coefficient of friction times the normal, which is basically a general case for the two specific frictions which you are going to use in this particular case. So for the condition of equilibrium to exist, the amount of friction in such a kind of a scenario is going to be just sufficient to prevent relative motion of the object. And of course, we are going to see that it's not going to exceed this specific value which you are going to refer to as a limiting friction. Now for us, we are going to use this concept of a limiting friction in order to define this specific aspect of the coefficient of friction given this specific angle of alpha. And therefore, we can have this specific friction by trying to define the forces which are going to be acting on that particular block. So the first force which we can identify acting on this specific block is the force of its weight. And in this case, we have defined this particular weight in terms of mg. So the second force which we can identify acting on this specific block is the normal force, which basically we have given in terms of n. And then we are going to have a third force, which is going to be the force of a frictional force given in terms of this specific representation. which is going to be given in terms of F. So therefore, we're going to create a relationship, especially for the two kind of forces for normal and friction, and try to see how we can have a relationship of that one with the weight that is being subjected to this specific direction at an inclined position. So since the body is in equilibrium, we're going to resolve we're going to do a resolution about this specific plane, whereby we're going to have this one represented in terms of their various trigonometric functions. So we can have the force represented in terms of mg, the sine of this particular angle of alpha. So this is going to be angle over alpha. And we can have this specific normal represented in terms of mg, the cosine over alpha, given as that one. So if we are trying to look at this one, then therefore we are going to have this specific plane resolved or resolving perpendicularly to the plane given as such, using the two representations which I've given. So therefore, for us to find this specific coefficient of friction from this limiting friction, we're going to have the ratio between F over N given in terms of this specific coefficient of friction. And if we try to look at this one, then therefore we can use the particular representations which we are going to have on the board, which we have said. But remember, from the condition which we are required to show this one, then therefore that one has an implication that we're going to have this one represented in terms of a value which is either equivalent to or of course greater than this value of a coefficient of friction. So therefore this implies that we're going to have F over N greater than or equivalent to the tan over alpha, which basically, as we said, the tan over alpha is going to represent this coefficient of friction which is been given as such. So from two definitions which we have made for the, of course, force and the normal, we're going to have this ratio given in terms of mg, the sine over alpha, divided by mg, the cosine over alpha, which is basically going to give us what we refer to as the tan over alpha. So basically implying that if this specific ratio is going to be giving us the tan over alpha, then therefore we can have this one given in terms of this specific ratio, which is the tan over alpha is basically smaller than or of course equivalent to this specific function which we have just given us that, which is going to be forming our final representation. So sorry for that, I've just basically done the opposite. So this is going to be just an equivalent representation for this one, for the coefficient of that friction, which basically still is equivalent to this one. And of course, we're going to have this one using those specific signs given in terms of this particular representation. So we had said basically that it's going to be either greater than or equivalent to that one. So there's a slight confusion somewhere. Need to find that one. And so basically, yeah, there's something wrong here. So basically, there's a mess from this specific point that I'm trying to follow up. So let's do it from this specific. So we can just do a direct rearrangement of this specific, of course, ratio between F and N from this. And this is going to be eta smaller than or equivalent to the value of the coefficient of course, friction given as such. And therefore, we're going to see that from this specific representation, we're going to have the mg, the sine of alpha, all over mg, the cosine of alpha is equivalent to, or let's just have this inequality sign being given as such. And as from this specific illustration, we're going to have this specific, of course, coefficient of mg cancelling out. Now the ratio between the sine and the cosine over theta, cosine over alpha, is going to be giving us the tan over alpha, which is smaller than or equivalent to the coefficient of friction. So in this case, this is going to be true for such a kind of an arrangement of an object which is lying on an inclined plane at an angle of alpha, and of course having a mass of m with this normal and the force. We're going to see that the coefficient of friction, which is going to be giving us the limiting friction, can be given in terms of the tan over alpha, is equivalent to or greater than that coefficient of friction given as such. So in this case, we're going to come across a range of evaluations which we are going to be following. And I'm going to kindly request our members to be passing through in case you come across such a kind of maybe some misrepresentation which is going to be following in between. Kindly put us or notify us in the comment section so that we can just do a rectification to ensure that our, of course, evaluation is accurate. So in that case, I'd like to stop there for today. Kindly check our description boxes for various links of other videos. Engage us in the comment section and also ring that notification bell for various updates in a different subject in mathematics and sciences. So that is it for now, guys. Bye, God bless you. Catch us in our next video.